One fun little application of the law of reflection is the so-called corner reflector, which is a box of mirrors. Each pair of mirrors meets at right angles. This is a drawing of a two-dimensional corner reflector, and it has the property that any ray of light entering the box will bounce around and leave along a ray that's parallel to the incoming ray. And you can show that with the law of reflection. These two angles have to be the same. Let's see here. How do we show that this angle is the same as that angle? That would have to be alternate interior angles. And then because these two are the same due to the law of reflection, these two have to also be the same. And it's not hard to show that the sum of these two is 180 minus the sum of these two. In other words, theta 1 plus theta 1 is 180 minus the sum of these two angles. And if that's the case, this ray has to be parallel to this ray. And that gets used, I think, frequently. There are labs in Europe, I think they're in Europe, measuring the distance to the moon by blasting a giant laser beam at the moon, because in the late 1960s or early 70s, I don't know which Apollo mission, an array of corner reflectors was set down on the moon. So let me screen share. You can Google an image. Here's a set of corner reflectors that were left on the surface of the moon. And to this day, laboratories bounce laser beams off of that set of corner reflectors. And the last time I looked it up, they were suffering from dust, which had accumulated on the reflectors. And that's making it more difficult to receive the reflected signal. Moving on, in the last video, I used the wave model of light to show where the law of reflection comes from, or that's one way of showing the law of reflection. Now I'm going to do the same thing with refraction, which is the bending of light. It really could refer to the bending of any wave, but we're talking specifically about light here. The bending at an interface between two different media. And I'll remind you that the wavelength of light in a medium is the vacuum wavelength, which I'll just denote lambda naught, divided by n, where n is the index of refraction. Remember, n is the speed of light in vacuum compared to the speed of light in the medium. And all you have to do is use this in combination with the fundamental relation between, let's see, frequency times wavelength is equal to speed. Of course, for E and M waves, the speed v would be c, the universal constant. So here's a drawing similar to the one that I used for the law of reflection. And because I've got a camera attached to a lamp post here with a rubber band, I can't easily slide this camera up and down. I think I'm just going to do things like hold the paper closer to the camera. If it works, it works. So just as before, these incoming rays would represent, call it a plane wave from a source that's very far away, which is why the rays are parallel. And the wave front, those crests and troughs, remember that they're orthogonal to the incoming rays. And 2 points here and here, directly across, they would be in phase. The phase at these 2 points is equal, even though the phase is changing. Remember, it's an oscillating electric and magnetic field, so the value of the E field would be oscillating here, but while they're both oscillating, they're oscillating in phase. And at the point where this ray strikes the boundary between material 1 and material 2, maybe this is air and this is glass, I've drawn a segment perpendicular to these two rays, which helps you visualize that this ray has to travel an extra distance before it gets to the boundary. It has to travel this much further, I've called it delta R1, than this ray has to travel. And this time, since we're not looking at reflection, I've drawn the refracted rays, the bent rays. Now it's true, some of this light energy will bounce off the surface. There's a combination of transmission and reflection, but we're only looking at the transmitted wave right now. And when you focus on these two rays, again, draw a line perpendicular between the two rays, and you can see that the first ray has to travel a little bit further on the other side of the interface. And what we're interested in is the total path length difference. So I'll call the extra distance that this second ray travels delta R1. That's, I guess I'm using different notation from the previous diagram. I must have gone with delta R1 because we're in material 1. And then the extra path length difference for the first ray on the other side would be delta R2. So the total path length difference, we just subtract the two. Okay, it seems I've gone with a slightly different notation for the vacuum wavelength, lambda vac. And we'll go back to the little equation that we used a lot in chapter 17. At any point on the transmitted side here, there's going to be a total phase difference for two adjacent rays. And that total phase difference has a contribution due to each of the path length differences. And since we're not looking at reflection, we don't have to worry about a phase shift due to reflection. If these rays are going to interfere constructively, then that path or that total phase difference has to be an integer multiple of 2 pi. It has to be 0, 2 pi, 4 pi, etc. And I'm looking for the condition of constructive interference because I would like to know if my eyeball was over here, in which direction would the light be most intense? If the intensity falls off rapidly as I move away from some particular angle, that would imply that I can only really see the light at that angle. If the intensity was distributed broadly, hang on one second. Sorry, I didn't want to sneeze directly into the microphone because the jury's still out on whether coronavirus can be transmitted through canvas. If the intensity was distributed broadly across a whole bunch of angles, then we wouldn't really have Snell's law. There wouldn't be one particular angle at which the light is refracted. But we're going to find that there is one particular angle. Okay, remember, to calculate each contribution to the phase difference, you take the path length difference and you ask, how does it compare to a wavelength? And then you multiply that by 2 pi. For instance, if the path length difference is half of a wavelength, this quantity in parentheses would be 1/2. 1/2 of 2 pi is pi. You would have a contribution to the phase shift of pi. Same thing for the path length difference on the other side of the boundary. So I'm going to add these up and set it equal to, it's hard to read here, set it equal to some integer multiple of 2 pi. And now let's divide the 2 pi from the equation. And I will rewrite delta R as d sine theta. So you've seen that d sine theta so many times. Even though here the geometry is a little different from multiple slit interference, we wind up with that same formula. So I'm looking at this right triangle here. And just like in my video about the law of reflection, let's assume that at the boundary of this interface, or at the interface between the two media, I'm imagining a line of atoms. Maybe this is the top of a sheet of glass, and we're just looking at it one-dimensionally, and there's a whole bunch of atoms regularly spaced. So D could be the spacing between each atoms. Don't forget, we're talking about light waves. Those are electromagnetic waves. What absorbs electromagnetic waves and what emits electromagnetic waves? That would be electric charge. And electric charge is often found around the nuclei of atoms. So as this E and M wave comes in, the charge distributions are forced to oscillate by the incoming electric field. And as they oscillate, they re-emit their own circular wave fronts, you could imagine them. Just imagine a whole bunch of circular wave fronts emanating from this atom, and from this atom, and from this atom. And as those circular wave fronts move outwards in all directions, we're looking at how they interfere. Do they interfere constructively in this direction? Do they interfere destructively in this direction? Okay, in this first right triangle, delta R1 is the hypotenuse, and that's what we're interested in. How about I off the side here? Here. Toyota safety recall. That's always encouraging. I'm driving around in a vehicle that has an airbag that doesn't work. D would be the side adjacent. Wait a minute. Okay, I obviously misspoke. Delta R1 is not the hypotenuse. D is the hypotenuse. If we take D and multiply by the sine of theta 1, we will get the side opposite theta 1. That's delta R1, which is where I got this from, right here. Do the same thing over here. You can look at the second right triangle. If you take the hypotenuse of D and multiply now by the sine of theta 2, you'll get the opposite side, delta R2. Now, how do I know that this is theta 2? Remember, we always measure angles from the normal. So the angle of incidence, theta 1, has been measured from the normal. And do you see, since we've got a right angle here, this is a right angle, that means this angle has to be 90 minus theta 1. And of course, this would have to be theta 1 again, because these two also add up to 90. Similar reasoning to arrive at the conclusion that this angle has to be theta 2. So strictly speaking, theta 2 refers to the refracted angle or the transmitted angle. It's the angle that the refracted ray makes with the normal. If this is theta 2, this must also be theta 2. Okay, we'll look more closely at this equation now. Why have I stuck in a minus sign here? Ah, right, because we need to subtract them. I drew a plus sign here, but remember, one path length difference corresponds to one ray, the other path length difference is for the other ray. We need the difference between the two to figure out how much farther just one of the rays had to travel compared to the other. All right, and what else can we do with this? Well, lower this. Remember that lambda 1, that's the wavelength of light in material 1. That's got to be the vacuum wavelength divided by n1. And it appears that I've changed my notation yet again, and I'm just referring to the wavelength in vacuum as lambda. Let me add a little subscript 0. Okay, so lambda naught over n1, that is the wavelength in material 1. The 2 pi's disappeared. And let's suppose now that this angle was known, that we were asking for light that enters a material at an angle theta 1 to the normal, what is the refracted angle theta 2 at which we get constructive interference? And I realize this focus is poor. This is the first week, so bear with me. I'm going to find some improvement on the visual quality here. Okay, let's solve this for theta 2. You know, in the last video, I actually solved it for theta 1. It didn't matter because the conclusion we arrived at was the same, which was theta 1 equals theta 2 for reflection. But in this case, it looks like I did solve it for theta 2. You'd have to move some stuff around. And you find the arc sine, 1 over index of refraction in the second material times n1 sine theta 1 minus. And here, once again, is that ratio that keeps popping up. Wavelength divided by separation between the sources. Again, when we did the lab for multiple slit interference, the separation between the sources, which was the slit separation, was actually much greater than the wavelength of light. But now we're talking about atoms, closely packed atoms, where this number might be something like a nanometer or less, and this number is at least 500 nanometers, or in the vicinity of 500 nanometers. So this is a huge number. Well, it's much larger than 1, which is what matters. Even if m took on the value of 1, the argument of your arc sine function would have to be something like 500. And if you ask Maxima, for instance, or Mathematica, or somebody who teaches complex analysis, if you ask them for the arc sine of 500, they actually could give you an answer, but the output of that function would be a complex number or an imaginary number, and we're not interested in that. We'd like to know what real angle has a sine of all this garbage inside the brackets. And no real angle has a sine of 500. So we're forced to set m equal to 0. In other words, we're looking at when the phase difference really is 0, not 2 pi. And if you think about it, I think would that mean that that this path length difference compared to this path length? No. The path length differences don't have, path length differences don't have to be the same. It's when you modify them by dividing by the wavelength, that's got to equal 0. Okay. So if you plug in m equals 0 here, what happens here? n1 over n2 why don't we just go back a step? Let's take the sine of both sides. Sine of arc sine, those two would just cancel. And so we work backwards one step to arrive at this result. And that's what you want to memorize. That is called Snell's law. I've just shown using interference that Snell's law should be true. If you're trying to figure out which direction in which the waves, the refracted waves, will interfere constructively, it's the direction given by this result. You can also write it in terms of the speed in the medium. You could have gotten rid of the N1 and written sine theta 1 over V1, where V1 is the speed in the medium 1, and over here you'd have sine theta 2 over V2. But I find it helpful just to memorize it one way. We may as well go with the indices of refraction. And this is applied all over the place. You can't do optics without this equation. You can't do astronomy without this equation, because we know that starlight bends as it enters the atmosphere. So when astronomers decide where in the sky a star is, they have to take into account the atmospheric refraction, and they use Snell's law to do that. Really, they use an integral of Snell's law, because the atmosphere is constantly changing its properties as you go upwards away from the Earth. So the index of refraction would also be changing. You can't explain the human eye without Snell's law, because your eyeball is filled with fluid. Ugh, so gross. Two different types of fluid. There's the aqueous humor, the vitreous humor. They each have their own index of refraction. Well, you'll see. There's lots of stuff in this chapter and the next chapter about that. So N1 sine theta 1 equals N2 sine theta 2. Why don't we immediately solve a problem using this result? I'm considering somebody who hunts for fish with the spear. I've never done that. That's a sport though, right? And I don't know what kind of fish people typically hunt for with spears. Could it be a salmon? That's just one fish for which I know the name. So let's pretend it's a salmon. And as this spearfisher is standing in knee-deep water, they see a fish that appears to be 3 feet in front of them. And we can show that if they were to thrust their spear in the direction that the fish appears to be, they're going to miss because of the refraction of light. So we'd like to figure out the direction that they should actually thrust their spear. Should it be behind the apparent location of the fish or in front of? Let's use Snell's law. Here's the water. Notice that the depth of the fish below the surface of the water was not specified. I'm hoping I don't need that. If I do, then I guess I'll have to specify that. But I'll pretend that the fish is right here, and here's my person. Okay, and obviously, if they can see the fish, the ray is going from the fish to the person's eyeball. Fine, I'll give them some arms here, short arms. I don't want to get in the way of the ray. Now we know that when this ray strikes the surface of the water, it's going to refract, it'll bend. And something I didn't talk about yet is which way it'll bend. So let me go back to the Toyota recall here. N1 sine theta 1 equals N2 sine theta 2. Let's think of theta 2 as the refracted ray. That's the angle that the ray makes on the way out. And I will solve for theta 2. First of all, sine of theta 2 is N1 over N2 times the sine of theta 1. And then we would just take the arc sine of that, inverse sine, N1 over N2 sine of theta 1. And it's not necessarily worth memorizing this, but what matters is if we're going from water into air, we know that the index of refraction for water is about 1.33, and that for air is 1. So this is a ratio greater than 1. That means we've scaled up the sine of theta 1 to a number bigger than sine of theta 1. And when you go to take the arc sine, you're going to find that theta 2 comes out bigger than theta 1. So as a general rule, and this is in your book, of course, you should try to memorize, if light is going into a medium where the index of refraction is lower, if N2 is lower than N1, then the angle with the normal will increase, which means that the light's going to bend away from the normal. So let me do this first. I will draw a ray from the eyeball to the surface of the water. And then I know it's got to bend towards the fish. And this is not a great diagram, is it? Because there's not a lot of bending there. But let's see if I can work with it. If a ray left the fish in this direction, when it gets to the normal with the surface, it will bend. And yeah, that difference just isn't great enough. So let me redraw this. Surface of the water. Here's the fish. And I'll make it more exaggerated this time. I'll draw the ray first. Okay. Here's the normal to the boundary between the air and the water. Air, water. And I know that this ray is going to bend away from the normal so that theta 2 is greater than theta 1. And I'll just put an eyeball here. Here's the hunter's eyeball. And as far as this person's eye is concerned, this ray appears to be coming from somewhere over here. So I'll draw a dotted fishy right here. You think the fish is here, it's actually closer to you. And many of you have experienced this if you ever owned a goldfish in a bowl. Is that still a thing? When I was a kid and you went to like county fairs and school events, they would give away goldfishes in little bags. Okay. I remember I bartered 2 goldfish for a Casio watch. That was a very proud moment for me in first grade. They're asking, or I was asking, if the fish appears to be 3 feet in front, where should they aim? Well, this would be the 3 feet here. How about I call that X1? And what I'm really interested in would be this distance, which I'll call X2. How far in front of the person is the fish in actuality? And I'm realizing already that this geometry is getting a little more complicated, but let's label some angles here. I'll call this theta 1. That's the incident ray from the fish to the surface, and then it gets refracted. That's angle theta 2. Okay, wouldn't this also be theta 2? This whole angle here would be theta 2. So I could call this theta 2 minus theta 1. Don't know if we're going to need that angle. But we've obviously got some right triangles here. Yeah. I suppose what we could do is figure out how this compares to this distance. Because we know that this total thing, this total distance is 3 feet. And we're interested in just this distance. Maybe I should label these differently, huh? How about, let's get rid of this. And I'll call this distance X1. I think that makes a little more sense. And I'll call this distance X2. It's getting a little cluttered here. So X2 is the adjacent side of this right triangle. And X1 is the side of this right triangle. Probably not adjacent. We'll see which trig function we're going to use. And I'll refer to the depth of the fish as H. Well, it might behoove us to add one more label here. I'll call this distance D, not the D that's been showing up in our diagrams like D sine theta. This is a label for the distance between where the person is standing and the point at which these rays exit the water. Okay, and I think what we've got is 3 feet is equal to D plus X2. Yeah, 3 feet is how far the fish appears to be from where the person is standing. And that would be this quantity x2 plus this unknown, unspecified quantity d. All right, and we are interested in this distance. That's from where the fish actually is to where the person is standing. And that would be x1 plus d, x1 plus d. All right, and now it's an algebra problem. We're gonna have to use Snell's law to relate x1 and x2. And I don't actually know where this is going. I just have a feeling that we should be able to solve this, even though we don't necessarily know the depth of the fish and this distance between where the person is standing and where the rays leave the surface. So from this right triangle, I can see that x1 would be h tangent theta 1. x1 is equal to h tangent theta 1. And x2 would be h tangent theta 2. If you don't see that, pause for a moment, pause the video and check what the tangent is using opposite over adjacent. Okay, we don't necessarily know what these angles are, but we do know how they relate. This is actually getting quite a bit messier than I expected. I think what I'm going to have to do is relate the tangent to the sine function because we know how the sines relate. I'm hitting a dead end with the way that I phrased this problem. I can identify from the diagram that x1 is h tan theta 1 and same thing for x2. And because I want to use Snell's law, I need the sine of thetas, not the tangents of the thetas. So I could use this fact. Tangent is sine over cosine, and I could rewrite cosine as the square root of 1 minus sine squared. This is already getting messy. Now, if I solve this second relation for h would be x2 over tangent theta 2. I could take this expression for h and plug it in here and write x1 as x2 over tangent theta 2 times tangent theta 1. And now I'll use this trig identity for tangent theta to insert in here expressions in terms of the sines of theta. x1 would be x2, and you can check if you want that this is legit. Now this is looking like something I can apply Snell's law to. Remember, the ratio of the sines is easily related to the ratio of the indices of refraction. Snell's law says that n1 sine theta 1 is n2 sine theta 2. So the ratio of sine of theta 1 to sine of theta 2 would be the reciprocal relation of the indices of refraction. That's a nice thing to memorize. If you want sine of theta 1 over sine of theta 2, you just flip the subscripts and use the ratio of the indices of refraction. So here I'd have an n2 over n1. What am I supposed to do with this? Okay, well, I could write theta 2 in terms of theta 1 using Snell's law, and then put this whole thing in terms of sine of theta 1, but unfortunately, I don't actually know what theta 1 is because the way I phrased the problem, I didn't specify the depth. So this is what you would call an ill-posed problem. We still got some practice with Snell's law. Could I rephrase the problem and make this much simpler? I believe so. We could say something like, what if the hunter appears or sees the fish in a direction that's a certain angle below the horizontal? So if we specify this angle, let's say the fish appears to be in a direction 50 degrees below the horizontal. We could use this right triangle to find theta 2, solve for theta 1, and then let me pause and see if that's something that would work. Okay, take two. I've rephrased the problem. Let's say that this hunter's eye is 4.5 feet above the water. I picked that distance by, imagining an average height person with water coming up towards their knees. And let's say that the fish is 1 foot below the surface, and that to the hunter, if they were to look straight ahead at the horizon, the fish appears to be in a direction 50 degrees below that. That should be enough information for us to actually answer this problem, specify the direction in which the hunter should thrust the spear. Now, how do we phrase the answer? We could say, figure out the direction of this ray from their eyeball to where the fish actually is and give that angle below the horizon, or just state how far in front of the fisher's body the fish is located. I think I'll go with the direction of this ray, which I'm not going to draw yet. But here's a ray leaving the fish, refracting at the water-air boundary. We know that it's going to refract away from the normal. This angle right here is what I'll call theta 1. This is theta 2, and we can easily see theta 2 has to be 40 degrees. We've got a right triangle here. So off to the side, I'll write theta 2 equals 40 degrees. And ultimately, let me go ahead and draw this ray now. When I say ray, I'm not talking about an actual ray of light. This is just a straight line from the fish to the person's eyeball. This does not represent a ray of light, because an actual ray of light would be bent here. But once I've drawn that line, I can see that we've got a right triangle here. And I know this distance. This is the 4.5 feet plus the extra 1 foot. If I could figure out what this distance is, then I could take the arctangent and get this angle, and then just do 90 minus that to get the apparent direction of, I shouldn't say the apparent direction, but the direction of the actual fish below the horizon. That's the direction in which they should thrust their spear. So how do I figure out this distance? Well, I need a good label for the distance between where the fish appears to be and where it actually is. So let me extend some lines here. Not to smear the ink too much. I need that distance because I think we can definitely find how far in front of the fisher the fish appears to be located. Remember, when this ray bends at the surface, the eye interprets the fish as being over here. If you wanted, you could draw 2 rays leaving the fish and refracting at the boundary and show that they both appear to be diverging from here. I think I'll do that diagram later, but your book does treat that exact same diagram in this chapter. Hopefully you know what I'm talking about because you've already read that. Okay. Let's look at this largest right triangle here. If this is 50 degrees, wouldn't this also be 40? This angle right here is 40 degrees. And I'm going to call this whole thing L. It seems to me that the tangent of 40 degrees is equal to opposite over adjacent, the opposite side being L, and the adjacent side being 4.5 plus 1 feet. So that would be 5.5 feet, and I can solve that for L. How far in front of the fisher's body does the fish appear to be? That's what I'm calling L. 5.5 feet times the tangent of 40 would give me a distance of 4.615. I'll just keep a few extra digits. Okay. The fish looks like it's 4.615 feet in front of the fisher's body, but we know it's actually a little bit closer. You may have experienced this if you ever reached into a fishbowl to grab a fish. I don't know why you would do that, but you're going to miss. You'd have to put your hand a little ahead, a little closer to your body than you might expect. So all we have to do is figure out this extra distance. What would be a good label? Maybe this is what I can call D here. If I can figure out what D is, I can subtract that from L to get the side of this triangle. I could get the distance, the actual distance between the fisher and the fish's body. How do I get D? There's a lot of right triangle stuff going on here. let's look at this right triangle. And remember, what's this angle? This total angle is the same as this angle, which is theta 2. Do we actually know theta 2? All right, we're going to sort this out. Okay, D would be, this is the 1 foot. If I take 1 foot and multiply it by the tangent of theta 2, I would get this distance. 1 foot times the tangent of theta 2. Well, we already know that theta 2 is 40 degrees. I'm sorry, I forgot to do the subtraction. It's 1 foot tangent theta 2 minus 1 foot times tangent theta 1. Yeah, I realize that there are many moments where the thing I'm writing is out of view of the camera. I will get better at this. Do you see what I'm doing here? I'm looking at this right triangle. If I can get this side, which would be 1 foot tangent theta 2, and subtract this distance, and I get that by looking at this triangle and saying 1 foot tangent theta 1, subtract this minus this, and that will give me D. Once we have D, we can subtract it from L and find the actual distance between the fish and the hunter's body. Okay, well, in order to do this, we need to know what theta 1 is. Take a guess how we're going to find theta 1. Yeah, you guessed it, Snell's law. N1 sine theta 1 equals N2 sine theta 2. I want theta 1. So theta 1 is the arc sine of N2 over N1 sine of theta 2. It's getting a little crowded here. The arc sine of N2 over N1 sine of theta 2. Let me just do this all at once. Because what is N2? This is the air side. I can just take the index of refraction to be 1. Since we're in water, the index of refraction for water will take to be 1.33. So I've got the sine of 40 degrees multiplied by 1 divided by 1.33. I hit equals. And then lastly, I take the arc sine. And my little computer here is telling me that the angle is 28.9. Theta 1 is 28.9. Does that make sense? It does, because we expect that angle to be less than the refracted angle. So now I can go in here and evaluate all this stuff. Since this is 1, I'm really just taking the tangents. There we go. Since the 1 foot, I'm really just taking the tangent of theta 2 minus the tangent of theta 1. Okay, so the tangent of 40 degrees, 40 tangent, minus 28.9 tangent equals, it seems that this distance D is 0.2, I'll round it to 0.29 feet. Okay, so the apparent position of the fish has really not shifted by much. That's about 1/3 of a foot. But I think 1/3 of a foot is enough to make you miss. Okay, so this right triangle now, I'm looking at this right triangle. This distance here would be the 4.615 feet that we calculated minus the 0.29. 4.615 feet minus 0.29 feet. This side would be 4.325. And I realize I should have kept more digits here if I'm using 4 sig figs here, or 3 decimal places. Okay, we're practically done here because now we know how far the fish actually is from the person's body. How do we turn that into an angle, for instance? I suppose you could just say, aim for a spot 4.325 in front of your body, but in practical terms, it would be easier to specify an angle. So again, we know that this is 5.5 feet, and we know that this is 4.325. How about I label this angle here? Let's calculate that angle. That would be the arc tangent of 4.325 over 5.5. 4.325 divided by 5.5. Take the arc tangent. That angle appears to be 38.1, really 38.2 if I round. And now we can specify how far below the horizontal they should aim when thrusting their spear. Now, is anybody going to do this if they're actually hunting? Nobody's going to whip out their calculator and calculate all these arc signs. I guess you would just acknowledge that the fish is going to be a little ahead and practice. Right? You have some intuition. 90 minus 38.2. 51.8. Well, you could just round that to 52 degrees. So the upshot here is, while the fish may appear to be in a direction 50 degrees, let's see here, 50 degrees below the horizontal, if you actually aim at 52 degrees below the horizontal, you'd be more likely to strike that fish. Okay, so the angular deflection is something like 2 degrees. And that would all change if we had gone with different distances, if the person was taller, if the fish was deeper in the water, presumably all these angles would change. Now, I'll point out that hunting this fish would be a lot easier if instead of chucking a spear or thrusting a spear, you were hunting with a laser gun. Because if you were pointing a laser beam at the perceived direction of the fish, your laser beam would come in along this direction and do what at the interface? It's going to refract towards the normal. It would just, it's like the opposite of what the rays coming from the fish would do. How convenient is that? That seems like cheating though. I don't know if there's any glory in hunting fish with a laser gun. Is that something you would brag about among other fishers? Okay, that problem is an example of a more general optical problem that your book addresses, which is refraction of light at a plane interface, and actually the formation of an image by a plane interface. So we're getting closer to the behavior of lenses here. I'm just going to go through the exact same procedure presented in your book. This time, let's imagine like a fish tank. Here's the boundary between the water and the air. Think of this as water, this is air, or it could be glass and air. I don't think I'd like to specify. Let me just label N1 over here and N2 over here. It could even be glass and water. Or if you're underwater, this is the fluid in your eyeball, and this is the fluid in the pool, or the water in the pool. And I will draw another fish here for definiteness, so we have something to think about. And then your book is going to refer to this normal line as the optical axis. Optical axis. I'll just make it solid. The optical axis. And the distance between your object, in this case the fish, your object, and the interface between the two materials, the plane interface, this is called S. You've seen that already when we were looking at the pinhole camera. So the fish is actually this far behind the interface, but we're going to see that it appears to be a little bit closer to the interface, and that image distance will be called S prime. So let's draw a representative ray from the fish to the boundary. Now, since I know this is going to bend away, let me make this angle rather shallow. Here's just a single ray emanating from the fish. Remember, there's an infinite number of rays you could think of, but I'm only looking at one of them. And in a dotted line, or with the dotted line, I will draw the normal to the interface. And think for a moment, if this actually was air, if this was air and this was water, wouldn't this index of refraction be lower than this index of refraction? And we know that when the angle on the other side is, when the index of refraction on the other side is lower, the angle actually goes up. The ray will be refracted away from the normal. Here's another way to think about it. If your wave is speeding up on the way through the interface, it's going to bend away from the normal. We know that the light speeds up as it goes from glass, for instance, into air, or water into air in this case. It's going to bend away from the normal. That's something you want to memorize. So I will draw a ray that's not bent too terribly much. This ought to be good. Here's theta 1. Here's theta 2. Okay. And we would like to relate the object to the image distance. If I extend this line backwards, this is a lot like the problem I just did. If your eyeball was over here, you would perceive this ray as coming from back here. So I will go ahead and draw the image of the fish. Now I've only drawn a single ray. I think later I'll go back and add another ray. The idea is, if you drew a bunch of rays coming out of this fish, if you look specifically at rays that are close to the axis, see how this ray makes a rather small angle with the optical axis? That's called a paraxial ray. Paraxial ray. So we're not interested in rays going off in this direction. We would see that all the paraxial rays, even though they be bent off in different directions, they would all appear to be coming from around the same point. So there's a whole bunch of rays that appear to diverge from this point, and that's the formation of an image. But right now we're interested in determining S. I don't know why I called this S1. I just want to call it S. And we're interested in finding S prime. And I will point out right now that the image distance for a virtual image is considered to be a negative number. So we think of this as a negative number. Why is it a virtual image? Because there aren't actually light rays converging here. If you put a piece of photographic film here, you wouldn't be able to develop an image of the fish. These rays just appear to be coming from this point. Virtual image. Okay, we have to do some trigonometry here. I've identified some angles here. The angle of incidence, if you use alternate interior angles, this would also have to be theta 1. And if this is theta 2, so is this angle. And that means so is this angle. So I'm now going to look at two right triangles. I've got the right triangle involving the apparent distance of the fish from the boundary. And I've got this larger right triangle. And would you agree with these two statements? The tangent of theta 1 is, I'm labeling this distance L. That's from the optical axis to where the ray hits the boundary. Tangent of theta 1 would be L over the object distance S. I'm using this big triangle. And the tangent of theta 2 is L over S prime. Fine. Well, these have L in common. So if I were to solve for L, let's see, right here I would have L is equal to S tan theta 1. Over here, L is equal to S prime tan theta 2. Those have to be the same. So I can conclude that S tan theta 1, that looks like Stan, is equal to S prime tan theta 2. What are we supposed to do with that? Well, it's not obvious from this diagram, but I'll try to make it more obvious. The angles that we're talking about, they're really small. It has to do with this assumption of paraxial rays. We'll come back to this in a second, but let me draw, I'll use the backside here. If this actually was a fish tank here, here's your little fish. If you're standing way over here, I know, I'm like Leonardo da Vinci here. I almost said DiCaprio. I'm definitely neither. Here's your eyeball. If this is the optical axis here, the only rays that are going to go from here to your eyeball are rays that are extremely paraxial. They're really close to the axis. Something like this. This angle's got to be small. any other rays that you might consider when they bend away from the normal, they're going to completely miss your eyeball. So the only point of talking about images is, for now, is images seen by the human eye. This angle's got to be, what, 10 degrees or less? And we know that for angles that small, for paraxial rays, theta is practically the same as the sine of theta, which is practically the same as tangent. If you don't believe it, put your calculator in radian mode and check the sine and tangent of some small angles, and you'll see that this is really accurate. You know, once you're down to 2 or 3 degrees, I think these are all the same to, I'm going to guess, 4 sig figs, 5 sig figs, which means we can replace tangent of theta 1 with sine of theta 1. And maybe you see now where this is going, because as soon as you see signs of the angles, we're talking about Snell's law. Okay. S prime, I'm going to solve this for S prime. That would be sine of theta 1 over sine of theta 2 times S. Great. So we can express the location of the perceived location of the fish in terms of the actual distance of the fish from the boundary. You should be recognizing here, we can replace this using Snell's law with the ratio of the indices of refraction. So just take the reciprocal ratio of the indices of refraction. S prime would have to be N2 over N1 times S. And lastly, remember I mentioned that in optics, we consider the image distance to be negative if we're talking about a virtual image. Well, this ratio is positive, so it's up to us to add the minus sign. And there it is. There's your first formula for finding an image distance given the object distance and the optical properties of the media, in this case, or specifically the indices of refraction. All you have to know is, for instance, 1 for air, 1.33 for water, and you can figure out just how much closer the fish appears to be. Let's do that real briefly here. For water and air, 1 over 1.33. 1 divided by 1.33, 3/4. Okay, I guess that's a fun fact to remember. If you're, what's that restaurant, Rainforest Cafe, where they turn on the fake thunder? I know somebody who knows somebody whose father used to be a manager at the Rainforest Cafe, and I guess one day the person in charge of the thunder accidentally turned it up to 11, so to speak, and the thunder was coming out of the speaker so loud, I guess all the little kids in the restaurant were crying. I don't know, maybe that story's been exaggerated a bit, but at the Rainforest Cafe, they have that giant fish tank. If you're standing in front of a fish tank, looking at one of those big fish with the giant lips, what's the name of that fish? If it appears to be, let's say, 75 centimeters behind the glass, we know it's actually full 100 centimeters behind the glass. Now you know.